presently too. Great.
Thank you. So, hello everyone. Today we'll be presenting on the paper A Strategy to Apply Machine Learning on Small Material Science Dataset, Metal Science. This was published in NPG Camp Computational Materials in 2018. I'm Naseem, and I'm Elson. We'll be mainly going over what the authors discussed in the paper and some limitations, and we'll go over the discussion later. So we have broken down it into several sections. First, I'm going to go over the motivation and background. Then the core discovery the authors described, the precision and 2D of association, and the proposed solution, which is the CEP. And Elson is going to go over and all the case studies and the interpretation and the broader meaning, and then we'll end the discussion with critique and discussion. Now, machine learning is an extremely powerful tool. It is it is largely developed to work on large data sets that has abundant data. For example, this is very common in computer vision, natural language processing, where there are millions of samples. And in that regime, machine learning increasing the data size also increases its efficiency by a lot. But material science is different. Most metal data sets are very small. They contain only few hundred data points, sometimes even fewer. And these data sets are not clean. Sometimes they're not uniform, they're not homogeneous, and sometimes they're expensive to generate also. And many properties require costly experiments or DFT calculations. And so we are expecting machine learning models that are designed to work on large scale data to work well on small data regime. That creates a fundamental mismatch between the machine learning requirements and the materials reality. This brings us to the main research question what the authors introduced, like how can we build accurate machine learning models when data is scarce? So at first glance, the obvious answer might seem to be like, why not just gather more data? But authors argue the main problem runs deeper than the uh, that they show that the limitation is not just the lack of data, it's also a statistical issue involving the model's complexity and bias, because in small data sets, a model tends to underfit because the lack of sufficient expressive information, and as a result it improves accuracy often improving accuracy often requires increasing model complexity, which introduces more of its own challenges. So the question becomes, how do we improve accuracy without simply increasing the data or the model complexity? So in supervised machine learning, the model tries to learn a function that maps its descriptors to its properties. For example, predicting band gap, thermal conductivity, elasticity modulus, etc. The key idea in machine learning success depends on detecting patterns from training examples. And typically, as shown in the learning curve all on the right side, we can see the performance improves as we increase the number of training samples, and more data usually means better generalization. So under normal circumstances, adding data helps, but in material science, as we rarely have thousands of samples, often only around 100, and that's where the challenge begins. So from a survey of prior materials ML models, the authors found that the prediction error decreases as data size increases, which is expected. And this follows a empirical scaling of power law, where the scale error is proportional to the size to the power of minus 0.37. So this means doubling the data size only reduces the error roughly by 20%. And this trend appears across different materials, properties, and different machine learning models. So it isn't just model specific, it suggests that fundamental statistical limitation when working with small data sets is also dependent on lack of physics knowledge. So to look at the key statistical concepts, first we look at bias versus variance trade-off. So total prediction error can be decomposed into bias squared, the variance, and the noise. So the bias occurs when models are very simple, and they also like it being very simple, it misses the true physics and results in underfitting. And variance occurs when models are too complex and the predictions become unstable and it tries to overfit it. So the figure on the right shows the trade-off as model complexity increases, test error follows a U-shaped curve, and these connects the degree of freedom which measures the effective model complexity, essentially how flexible the model is. Balancing these two is the central understanding of the paper and their main discovery. Now, what that when the data is limited, as improving prediction accuracy requires increasing the model complexity. In other words, the model has to become more flexible. So as the model becomes more flexible, it needs higher degree of freedom to reduce the error. And but on the right, as you can see, like when the data size increases, the cross validation error decreases, and this creates this creates what author claim the precision to DOF association. So for better precision is strongly linked to higher model complexity. So accuracy improves, but only at the cost of making the model more complex. Now, precision DOF association happens because these models are underfitting and the error is dominated by bias. The authors quantified these by the bootstrap analysis they did. So they found that the bias is around 0.26 EV squared and the variance is 0.06 EV squared. And the majority of the prediction error comes from the bias, meaning the model is missing important physical information. And the mediation diagram on the right shows that the data size affects prediction error mainly through the changes in model complexity or DOF. So the problem isn't noise, it's missing physics. That's why simply increasing the model complexity reduces error and it compensates for the missing information. Now, this precision DOF association creates a serious problem. When data is small, machine learning compensates for missing physical information by adding more parameters. In other words, the model itself becomes more complex just to reduce bias. But this makes the model complex without necessarily making the truly predictive. And this has consequences. It hurts generalization. So the model may not perform well on unseen samples, and it reduces interpretability. It becomes harder to understand what features actually matter, and it is and most importantly, the limits it limits physical insight. So we don't learn meaningful in scientific relationships. So simply increasing the model complexity is not sustainable solution. So this leads to the core idea of the paper. Instead of adding more data or increasing model complexity, the authors propose adding better information. They introduced the CEP, which is Crude Estimation of Property. This is a simple idea that is included as a physics-informed approximation prediction to the of the target property as an addition to the feature in the model. So CP just needs to capture the meaningful physics trends. It can come from empirical models or any chip simulation, approximate theory, or low-cost experiments. So instead of asking the model to rediscover physics from scratch, we guide it with the physics we already know. So CP works in two simple steps. First, we compute the crude estimate of the property using an approximate physics model. Mathematically, this can be written as YCP, which is HX, and HX is the approximate physics model, which can be determined by any cheap, fast, imperfect real correlation with the true property. And the second part is the augmentation with machine learning model. In this part, we include the crude estimation as an additional input to the machine learning model instead of only the data we have. So instead of just inputting y equal to f of x, we give the model y f equal to f of x with the predicted with the crude estimation as a separate column. And equivalently, we can think of the true property as a crude estimation plus a correction form delta x, and the machine learning model now only runs the correction form rather than the rediscovering the full physics from scratch. So as long as CEP captures the overall physics trend, it provides structure to the model. And by including CEP, we narrow the hypothesis space and we reduce bias and encode the meaningful physics directly into the feature set. So the model is no longer in need of high degree of freedom just to rediscover basic physics relationship. Now one might think is this just multi-fidelity? So this is related but even simpler. So in multi-fidelity modeling, low and high fidelity data are modeled jointly in hierarchical way, but here we simply use low fidelity prediction as an additional feature. So
I'll go ahead to describe the three case studies that the authors used in their study. So for the first case study, it's trying to predict the band gap, and the setup looks like an input data of 108 experimental data points. And the model they use in their model, they use the kernel ridge regression to make the model, and the features were chemical descriptors from the 108 experimental data points. And the CAP that was used to augment the model was basically the generalized gradient approximation, which is, a computationally cheap simulation technique. And then they went ahead to validate with the LOO, which is leave one out cross validation. And they compared several metrics to, decipher what the performance is. And the results, first, you would see these two charts. The first chart there is basically the predicted band gap versus the experimented band gap. And you'd observe a much tighter, linear curve there. Using the key, you'd see the model with CEP, the one without CEP, and just the CEP by itself without any chemical descriptors. And you'd observe that the one with the much tighter trend is the one with CEP, indicating that CEP helps the model. And then the other charts you see there is just the CVRMSE, root mean square error, versus the correlation. And what they tried to do here was they added some noise to the data, and they were trying to find at what point does the CAP help our model. And they find out that as long as the correlation is above 0.5, the CAP is going to help the model. There are other metrics, like we already discussed, the root mean square error was reduced by 33% after CAP was added. The scaled error was also reduced from 9.3% to 6.2%. The degree of freedom was reduced from 12 to 9, and visual trend is very obvious to see. There's so much, there's a large deviation before CAP, and then you find the linear trend after CAP. The authors also decided to compare with other reports in the domain. They did two particular comparisons. First one was with Lee et al., where he did some work on inorganic compounds, and their CV error was 0.18. The other hand, Kailania et al. Worked on L-pasolites, and basically they got an error of 0.1 to 0.2 EV. And you'll notice that these error values are considerably lower than, our model after CEP. But the authors were able to, explain why we have that with 2 points. First, they both works add computational calculations as their input data, whereas theirs were experimental data. Basically, you would expect such errors from experimental data where there's human error, there's instrument error, and whatnot. And then also, one of the work, the one by Pailania, basically just worked on a particular class of materials, and that reduced the degree of freedom in that example. And in general, the higher the degree of freedom in the configuration space, the more challenging it is to construct an accurate machine learning model. And then we'll go to the second setup. Yeah, so they imputed a data set of 93 experimental data points, and then the model and the features, just like the previous one, was based off kernel ridge regression. chemical descriptors from the 93 experimental data points, and the CEP in this case was a slack model combined with a unified Grotescian parameter. And the validation, just like the previous case, was also the leave one out cross-validation, and they compared certain metrics to examine what their model performed like. So in this case, just like we saw in the first one, there's also a very tight linear trend, and the scaled error reduced from 6.2 to 4.1, and the degree of freedom also reduced from 7 to 5. The authors also compared with a framework that already exists for calculating lattice thermal conductivity, which was the Debye-Callaway. And they actually found out that their model did better than this that already exist in the domain already. So that also proves their point that CEP works better with small data sets. And then they also decided to classify their data sets into simple structures and complicated structures. And they arrived at the conclusion that with simple structures, the model will do better, and with complicated structures, the model will do, slightly less better. The AFD, yeah, is a metric that is used to, is a statistical metric used to evaluate the accuracy of a model when the target property, in our case, is the thermal conductivity, spans several orders of magnitudes, where you can have 0.1 and then have 2000. And that's the mathematical expression right there. The next case study 3, was the elastic modulus of zeolites. And the setup, we had 102 data points. And this time they used a gradient boosting regressor to make the model. And the descriptors were local structural and porosity descriptors. And the CEP that they added were, force fields calculations for the target properties, which was bulk modulus and shear modulus. The validation was done by threefold cross validation, and they examined the performance matrix in this case. What they found is that in general, the adding CEP to their model would improve the precision with the root mean square error, and it will reduce it by 50% approximately. So what you see here is five different force field calculations, and that was what made up the CEP. And then this bar there represents the model without CEP. And you see that all of them consistently gave like a 0.5 or 50% reduction in the arrow MSE. And then, of course, just like we already mentioned, the 50%, the scaled error also reduced by about 50% from 13% to 6.1%. To summarize our findings, what we find is in 3 case studies, the usage of CEP is consistently found to boost the predictive capability of these machine learning models. So what that means is that it can be a general approach to help small data sets. From what we have observed, there's going to be some conceptual shift. And the first one we want to talk about is from quantity to quality. When data is scarce, what do? We don't just need to go and make more data or, force the computer to make a model that finds, physics that is not already there. What we can do is add an extra quality data that reduces the model load, and then, increase the accuracy of the model. In that case, accuracy becomes a function of the data size plus what we already know about that particular domain. Another conceptual shift is from pure to augmented. By augmenting machine learning models with what we already know, we no longer ask computer to discover physical laws from scratch. Basically, human-derived models that already have errors that seem like they are crude become useful when you combine them with the computational power of computers. So accuracy in this case becomes a combined function of what humans already know with what computers can do. What this means for us, now we are able to find a strategy that both gives us high predictive accuracy, and it's low in computational cost, as against pure empirical models, which gives us low accuracy, and pure DFT, which would cost high computational resources to arrive at. We found some limitations with this method, one of which is the fact that CEP is domain knowledge based, and a CEP that works perfectly for semiconductors, for example, might not just work very well or may be completely irrelevant for metallic alloys, polymers, and other classifications of materials. Like you'd observe, the three different case studies we looked at, they had their own different CEPs, so we can't just take what we know from here or a CEP data set and put it here. So that's one of the limitations. Another limitation is the fact that the entire model then depends on the quality of the CEP. If you use bad CEP, it can be a source of potential noise. The key takeaway from this is the bottleneck in material machine learning is not just that we lack algorithms, it's that we lack physical, meaningful information per data point. Each data point has to describe the physics behind what we are doing. And from there, machine learning doesn't just need to make up physics from the scratch, but it's able to determine or find what patterns exist from what we have given it. By adding CEP, what we can do is reduce bias, avoid over-complexing the model, and enable machine learning to work with realistic data set sizes, which is what we have in material science at the moment. Yeah, thank you very much. We are now at the discussion points, and from your contributions, we were able to bring out these 5 questions that we would like to discuss together. The first one is, how would CEP work with large data sets? This paper is already focused on small data sets, and we have seen how much considerable value it adds. So, but it will be interesting to know what we think about large data sets. Does anybody want to? Yeah.
I think it could still have an impact, but I think it would be less significant as it would be with smaller data sets, because when you already have a large data set, I guess there's less of a need, but I guess adding it would probably not hurt what you're trying to find.
Thank you very much. Any other person? Yeah.
Actually, I wonder if like adding a CEP would be more costly for a large data set, just because like you have to have the time to run all those calculations
Yeah, that's another consideration.
set, and then also do machine learning on the side. So then would the cost be higher technically?
And then that defeats the entire purpose of CEP, because CEP is supposed to be cheap in the first instance. Yeah.
And I think something else, like even within the 3 case studies, they use CEP to like describe all of them, but a lot of the methods are like they range in how computationally expensive they are. So I'll just, I guess, case by case.
Yeah, it's case by case.
So I think your point is like both of your points are right. Like, so you have to find a balance somewhere. Like when you start calling a data set small to large, like you have to find a balance, because if implicitly CP has 2 problems. One is actually finding CP, finding a crude model that should apply. Second is how good is it? Like sometimes it can be very bad, doesn't really relate to the manual set. So if you introduce a bad CP in a large data set, it's going to ruin the data set you had from earlier. So it's actually introducing more noise to the data set. So machine learning will face more problem while learning it. So actually in large data sets, as we found and we saw in different papers, they don't actually care about CP that much when the data set is large enough, because it doesn't add more knowledge, because it's just a crude model, not anything accurate or more realistic physics.
For large data sets, basically there's already enough physics in the data set for the model to find patterns. And so CEP doesn't really add much value, or the value just disappears, you can't really find it anywhere. The next question or next discussion point would be, what happens if there is no CEP data set for a new material system. This question is very interesting. What happens? We've already talked about how it may be expensive to just add more data, or that may not just be the case. And CEP kind of, provides like a very good solution. But then you don't have CEP data to add. There's no extra scriptor that gives that quality we need. What happens in that case? Yeah.
Then you just await like until experimentalists are able to develop some sort of empirical model, and then you're able to default to see. Does it just mean that there's like a buffer time where you have to wait on CEP to become valuable? I imagine that's the only next step.
Yeah.
Then there is a problem
Okay.
with like simultaneously experimental group will have to work on the same data set. So that's like sometimes likely, most of the times very unlikely.
Increase complexity a little bit, maybe to like make it, let's see it more precise results when you have slightly more complexity.
How do we increase the complexity?
Like adding more degree of freedom.
So that's going back to our point, more experiments, more going back to the lab.
What we thought is like if CP doesn't exist, then this method actually is not going to apply to that data set. That's about it. Maybe I don't.
Yeah.
The CP don't exist, then this method is not going to apply.
If CP doesn't exist, then this method is, you just cannot use it, basically. You have to do some more experiments, or make an empirical model. The next would be, if the model leans too hard on CEP, are we really learning anything new about the materials, or we are just repackaging the baseline estimates in a fancier way, calling it CEP? Yes, please.
I mean, with the CEPs themselves, they were never like perfectly accurate. So I think when you look at like, I guess how effective introducing a CEP is, it can also tell you, I guess looking back at the CEP, like let's say there's something from the past, how close they were to accuracy with that too.
Yeah.
It all depends on, I guess, the type of CEP though.
Basically, CP is just another descriptor, although in this sense, it acts like a super descriptor. And because there's so much patterns and so much physics in that one extra data set, like we saw in this slide, yeah, you notice that with CEP, without CEP, and just CEP alone, you have all of this. So there's some learning going on with the other chemical descriptors, the other columns in your data set. So we're actually learning from the CEP. It's not just another fancy way to express. Okay. How can you prevent addition of bias to the crude data if you are severely over or underestimate in your crude approximation? Does anybody want to help out?
This was like more like baseline question, like more like how the model works, what is input. So we don't have much idea about this, so we don't add anything behind this question. If anyone has any idea or knowledge about this, just feel free to.
Just like the way the empirical models are derived, there is an inherent like bias and like, access to like certain reagents or something like that. And so inherently your like empirical models will have some sort of bias. And does that result in just like a further bias in these eventual CEPs? I imagine it does. I don't really know if there's a good fix, but I think it does. And I think that's something users of like MVP have to be wary of.
I have a question about how like this whole thing works. So when the model is getting, I'm assuming trained, does it know the crude data is a crude data, or is it just mixed with
Yes,
the actual
yes.
data? Okay. So
And
the
then
thing
it
was-
tries to get the difference between the model itself and the crude data. So the delta
Right.
X, it tries to learn the delta X to find the pattern. So it knows that the pattern should look something like the crude data, but not exactly the same. So it tries to find the difference between the data points and the predicted crude data to find and learn why there is a gap and tries to estimate the correct.
So I wonder if the reason it's not biased, it's because you're relatively seeing the pattern. You're not trying to exactly match the data, but you're just looking for relative trends.
Okay. I will just go to the next point. The paper mentions that CAP doesn't need to be accurate, just correlated. Can we make a synthetic CAP that doesn't rely on physics and is just correlated? It's a very interesting question. Like, just make up stuff.
So what we thought in this question is, like, if you just make a synthetic CP, you're going to make it based on the data you already have with the data set, and that's not going to add anything new. And like, machine learning is going to do it itself. So if you don't have any like CP that is like actually based on any physical property, it's not going to help making up a correlated CP. Like you need actual CP to help the machine learning.
You imagine in this case that you'll have like overfitting?
Oh, yes, it will result in overfitting.
Yeah. Basically, there's no physics to that the model learns from.
Yeah.
No, there's nothing to learn from. So it's either you are creating new noise, even though it's correlated, it's either you're creating noise or something that retracts from the physics in the other descriptors that you already have existing, you know. So it's not recommended. The whole idea of CEP is that it is a crude approximation of that property that you're looking for. Yeah, so if there's no physics underlying in that extra data, the quality is not great, and you practically would ruin your model. Yeah, that's all we have, and thank you for coming to our TED Talk.
Great presentation, right? So I hope you all enjoy the paper. Can I just go back for a while? Okay. Can I ask a question to everybody just to make sure that I understand this clearly? Let's take an example, right? Whatever, elastic modulus of zeolite, right? So they had some input data, which means they had some true elastic modulus. You all agree? They built these descriptors, right? They call this local structural blah, 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 CP, right? And nothing else in, and everybody, and Nasib covered beautifully. So, and there was a little bit of a discussion about the delta X, right? So help me here. Did they actually, what was this paper about, right? So is it Y is equal to f of X, comma, YCP, or is it delta, or whatever delta, is equal to f of X, right? Where delta can be defined as Y through minus Y CD. So which one is correct? What is going on in this paper? Do you see my point here? Right, so this is a supervised learning model, right? Y, you're predicting Y as a function of inputs and the CEP. But then delta, which is defined as the true value, the 102, and you have the CEP, so you can actually subtract it and you can get a delta. are they learning this one? What is going on in this paper? You see my point? What is your take?
I think it's learning the difference between like,
So basically, they're fitting a model to learn the delta. Is that correct? Is that everyone? Is that what everyone sees? Because that's not the way it's written there, right? So
I think it's the upper one.
yeah.
Yeah, I think so.
All right, now we need to talk a little bit about it. So, so how many think this is the way it was done? Did you pay attention? Yeah, right. So 1, 2, 3, 4, 5. Okay, and it's like evenly 5 the other side. So, all right. So just both are valid way. I cannot say one is good, one is bad, right? But I'm curious from your perspective when you read it, because these are different. You're learning completely different things here. Right? So that was the first point that I wanted to clarify with you all. Okay, so it seems there is confusion here, right? So the other thing, a broader thing that I wanted to say is, as you all know, there is a final project in this class. When you're reading papers like this, which is a technical article, this is not a review, right? And you pay attention to how the authors are building their data sets, right? Because that's going to be a very crucial factor for your project, because essentially you will bring a data set with you for the project. Hopefully reading papers like this and the one before, not just the way that it was written and the questions that they wanted to address, also about how do they construct this data set? Where did it come from? If you have, maybe 10 to 15 minutes of your time to process that information, my point being, that's going to help you build your own data set. When push comes to shove, right? When we reach somewhere the mid-March, when we start really thinking about project, I think it's going to help us a little bit there. So okay, so that's one of my requests to you all to think through that. Okay, good. So, and maybe I'll just get distracted a little bit, and so that was the first thing I wanted to. So this is materials informatics, right? So, and you also know there is a big field called as bioinformatics, right? So, the common thing between the two is informatics, but one is bio, the other is materials, right? So, as material scientists, chemists, chemical engineers, so people interested in physical science and chemical sciences of the world, right? So one key thing that we should always keep in mind is, we have these machine learning models, right? How do we make it personalized to the problem that we wanted to solve, right? So how do we make informatics materials informatics, right? So I think this is a very critical question for you all to be thinking about. We will introduce some strategies to basically address that. But I thought this was an interesting paper, taking a slightly naive approach to bring in materials to informatics and calling it as a materials informatics. In this case, they relied on some existing simple empirical models, right? So to define the state of knowledge, and then use that to augment their other heuristics, which no one knows what it is. They hope the model does something, right? But they were at least cautious, and they were able to bring that concept to this particular paper, right? So which was really interesting in my opinion. So, irrespective of a big data size versus small data size, I think the fact that they were able to bring in some knowledge to the problem, I think that was really cool. Which I appreciated when I first saw this particular paper. Right, I mean, one thing, this is something that I want you to always think about, right? So I always believe that machine learning is nothing but garbage in, garbage out, right? So if you're not spending time incorporating what you think your understanding is, the understanding of the community and so on and so forth, inadvertently, we add a little bit of bias to the whole issue, right? until then, it's very difficult for us to solve important problems. So those are probably one thing that I want you to keep in mind, right? So along those lines, right? So maybe one final thought. The way I like to think about this, and I don't know which one resonates in this class, right? So let's say you have an X input, okay? And then you give this input to a model, right? And you get Y, right? So there are two ways to look at this particular paradigm, right? The first paradigm is all you care about is Y, right? You provide some X, you want a Y. The hope is the Y is a pretty good Y, right? So that you can, discover something new, something interesting, graduate, get a paper, and do fun things, right? So that's the first paradigm, right? So I'm going to call this prediction. You don't care what goes in, you don't care if it's a simple model, complex model, blah, blah, blah. All you care is a good Y. That's it. It fits, gives me good predictions, I'm happy, I move on, right? So that's a prediction problem, right? So there is a slightly different problem. It's called as a science problem, where you begin to ask the question, like, why did it work? Like, what is it learning, right? Probably in this case, you don't generally care about what comes out. It need not be perfectly accurate. It can capture broad trends, but what you really care about is what's actually going on inside of this particular model. Like, why did it actually work? Why am I getting a prediction that I care about, right? So, which box do you all belong to? Well, which category? Is it prediction? Fine. All right. So how many say one? Okay. There's nothing wrong in both, right? There are two ways to thinking about this problem. I see two hands raising one. How many say it's two? All right, okay. A few, some are agnostic here, right? So just completely fine. So for those who say this is the most important thing, why do you think so? Please, yes.
Well, I think that this is kind of on a project by project basis. So the reason I said prediction is currently my lab is trying to use machine learning to get a certain output, but later we may do another project where we're looking at a science aspect, where we're trying to make good models.
So you're saying this depends.
Yeah, like on what project you're doing. And
anyone has a slightly stronger opinion? Yeah, please.
I think in maybe the context of material informatics, a lot of like the two papers you read so far for
Right.
this, they're using like well-known types of models already. Like, I don't remember exactly which ones they're using, but like Ridge is like one of them. And so there's science that goes into from like more computer science perspective, how like that model interprets data, turns things into vectors.
Right.
And so you're trying to see if that was an appropriate model to use to get a good Y.
That's a great point, right? So we will sort of address that in a much more detailed way when we do the supervised learning, right? So when you choose a model, you basically also choose the bias associated with the model, right? So I think when we do supervised learning, we will approach this through the lens of 3 points. One is called as a hypothesis space. One is called as a loss function. And the third is the optimization, right? So these are the 3 key things that we will be always concerned about when we train supervised learning models. And whether it is random forest, which we saw in the previous paper, versus ridge regression, which we saw in this paper, they will have some subtle differences either in the hypothesis space or in the loss function, the way they compute, or in the optimization that they've actually performed, right? So we'll conceptually get a better idea of all of that. But I see your point, right? So there is some science that goes into this particular phase, right? So, but my bigger point was, at the end of the day, we hope we learn something new, right? So that we create new knowledge, and when I was saying science, it was basically the new knowledge from the perspective of the material science community. Right. So for the other folks who think science, what do you think that is important for you? Yeah, please.
I think science is important because it ensures that the model is not very specific to the data set. So in a sense, if you are just okay with prediction, you can, like, the model can be so different for different data in the same domain. It can actually be very strict on that particular data set. Whereas if there's science, which science has some learning to it, it learns what it needs to learn and it can apply it in another data set. So that's what I think science is.
So interesting aspect, right?
It's kind of what I was trying to say too, in that if you don't know how it works, how are you gonna know where else to apply it to? And like, then your study isn't replicable, in that if you don't know where else to apply it to, you're not gonna be able to trust that you can get a prediction that's accurate in another data set. So
That's a fair point as well, right? So please, yes.
So I have a different perspective to it.
Sure.
So normally what happens is with the traditional models, we can arrive to a predicted result and everything. So, but what I always have seen is like experimental values are always far off compared to the predicted values. So by improving on the models that we already have, we can make a better predictor. But the results are the things that come later. Like if we don't have a good model to actually predict something, the results are as bad as not having any results.
Right.
So that's why I feel like with the models that we have, improving on that models is more should be more prioritized than getting to a result at first.
I see. Okay. All right. Thank you. Right. So, whenever you see a machine learning lecture, I hope just think about this idea, see what the author actually is trying to say. Once we put it in this particular paradigm, then we can ask some interesting questions, and this leads to some new discussions to be had. All right, perfect. So lead 2 is done. So how are we enjoying lead so far? Too much work? Too little work? Or
For sure work.
I don't know, every week you read one paper, right? So I think to me, it's fabulous. So in addition to many things that you do, right? And it's not only you have to read, you have to actually write about it. It's time consuming. I completely give that to you. So let's finish this one round of 5 leads, right, with the whole class, and then we will reassess what do we want to do, right? Should we have another round of leads, or should we do something else, right, which makes it fun for you, right? So, and I like this because the class is a bit more lively through leads, because you present, you discuss, you talk, rather than me talking on Tuesday, where you have a little bit of energy, but Thursday, boy, the energy is low. So we need to figure out how to make that more energetic and exciting. So we'll see, right? So now I've been enjoying everything that you've been writing, the presentation. So I think presenting is a very critical skill set. So summarizing a paper is also a very critical skill set. Already you're all talking about bias variance trade-off, and we will all study that in some depth in this class as we move to supervised learning, idea of complexities, and so on and so forth. So it's good that you're mentally ready for what's going to happen in the latter part of this particular class. So this is good. Yeah, there are a lot of issues, but hopefully by the end of this class, you'll have a slightly better critique of how to think about ML. Maybe you'll have your own perspective of it as you apply it to your own data sets, right? So, sorry, please, yes.
question. So which of those was it? Is it the first one that they're trying to do, or is it the
My
second?
understanding is the first.
Okay.
Right. So they augmented, which is why they care about correlations, right? So it simplifies what the model has to learn, right? And I could be wrong. Maybe this is not a bad idea as well. So When you think about a CEP, right? If you are in the field, you can recognize some of the names like Slack and Debye-Callaway. So they're all very popular empirical models out there, analytical models out there. So, and they are based on severe assumptions, right? So they don't work for all classes of crystals. So they do correlate, right? But they may not explain the entire data set. So modeling the difference and really augmenting what Slack missed and understanding the new contributions that the Slack missed is not a bad idea. So doing this is right. Please, yes.
Yeah, I actually read somewhere that doing that second, that you described is a way to prevent CP from being so biased in it. So when you find that CP is just a crude estimate, you can do some evaluation where you take the difference between the model, what the model predicts with CP and the actual values. Take the difference and then add it to the CP or add it in some mathematical formula. And it gives you closer to
Right.
the target.
So you need to think about bias in a slightly holistic perspective now, right? So when you commit to a CEP, you're actually biasing your data set right away. You may sort of reduce the statistical bias, but you're actually introducing the physical bias into the system. So we have to be careful. Is that what you want, right? So what is the ultimate aim, right? So the ultimate goal is to predict something new, right? I don't know if they demonstrated any new in this paper based on the approach that they did. So it should be go back to the first sort of lead example. They spent a lot of time talking about the local CV so that you can extrapolate beyond the data set that the model is trained on, provide a more rigorous estimate of extrapolation, right? So it'll be interesting to check if this approach can extrapolate, or is it going to be biased by the CEP itself, right? Because at the end of the day, when you train machine learning, it only knows correlation. It does not know causation. And that's an interesting thing to be worried about. So